Okay, let's get started. Welcome, everyone, to the deep dive.
Great to be here.
So today we're diving into something pretty cool, I think. It's about how uh, mathematics, specifically calculus, differentiation, integration, how those concepts actually pop up in the real world.
Yeah, in living processes,
Mm.
we've got this source excerpt, and it looks at something, well, incredibly down to earth. How plants take up nutrients.
Right, nutrient uptake. Seems simple, but the math behind it is interesting.
It really is. Our source, it focuses on modeling the rate that plants absorb nutrients, from fertilizer specifically, over time.
So it's taking calculus, which can feel a bit abstract, and like you said, rooting it firmly in the soil.
Right.
Literally.
Exactly.
Okay, so our mission for this deep dive is basically to unpack that connection. How does the math, maybe stuff you're learning right now, how does it actually provide a language to understand these natural processes?
And we're zooming in on that specific bit from the source,
Yeah.
using a derivative to model the rate of uptake.
Yeah, the rate, that seems key.
Well, what's really insightful, I think, from the source is how it stresses using a derivative here. Because think about it. When you put down fertilizer, the plant doesn't just hoover it all up at one steady speed, right?
No, I guess not. Things must affect it.
For sure. Soil moisture, temperature, even the plant's own growth stage.
Mm-hmm.
All that stuff changes how quickly it's grabbing those nutrients at any particular moment.
Okay, so that's where the derivative clicks in.
Precisely. If you imagine the total nutrient absorbed over time as, like, a quantity building up, the derivative of that quantity tells you the instantaneous rate it's building up, how fast it's happening right now.
Ah, okay. And the source shows how modeling this rate gives a clearer picture than just looking at the total amount absorbed over, say, a whole season.
Exactly. Understanding the rate is super important, especially in something like agriculture. Why?
Well, I'd imagine knowing the rate helps with timing.
You got it. Knowing that rate lets you manage things much more precisely. You can figure out, for example, when the plant is absorbing nutrients most efficiently. Find that peak rate.
And that insight comes straight from the math model.
Yep. And it tells you the best time to fertilize, maybe.
Yeah.
Maximize uptake, minimize waste, less runoff into the environment. It's about getting specific and quantifiable.
Moving beyond just a general sense of the plant needs food to knowing when it's hungriest, essentially.
You could put it that way, yeah.
Okay, so the derivative is like the speedometer. It gives us the speed at any instant. But the source is about nutrient uptake. Often, what you really want to know is the total amount absorbed over a certain period, right? Like during a key growth spurt.
Mm-hmm. Good point. How do we get from that instantaneous rate back to the total?
Yeah.
Well, that brings in the other big player in calculus, integration.
Ah, the other side of the coin.
Exactly. If the derivative gives you the rate of change, integrating that rate function over some time interval,
Yeah.
that tells you the total change during that time.
Okay, so integrate the speed to get the distance traveled, basically.
That's the classic analogy, yeah.
Yeah.
Here, you integrate the rate of nutrient uptake, say, over a week, and it tells you the total amount of nutrient the plant actually absorbed that week.
Right, connecting the dots now. So the source probably uses both differentiation and integration for the full story.
Very likely, yes. You differentiate the total uptake function, or you model the rate directly to understand the speed. Then you might integrate that rate back over time to calculate the total amount absorbed.
It's like a mathematical toolkit.
It really is.
Mhm.
And this isn't just, theoretical stuff on a blackboard. Building these models, often using real experimental data, lets researchers and farmers actually predict things.
Like what?
Well, predict nutrient availability, fine-tune fertilization schedules, compare different types of fertilizers, see how, say, a drought might affect uptake.
Wow, okay. So it turns these math operations into really concrete tools of improving farming, maybe even helping the environment.
That's the goal. Better practices, more sustainability.
It really is fascinating seeing how concepts you study, finding a derivative, doing an integral map directly onto something so dynamic, like a plant feeding itself.
Yeah.
It's just calculus isn't just about, curves on a graph. It's fundamental for describing change and accumulation everywhere.
Absolutely. And this example, nutrient uptake rate, it's just one instance. Think about anything that changes over time or builds up over space.
Yeah.
Chances are, derivatives and integrals can help describe it.
So wrapping this up, what's the takeaway for you listening? If you're grappling with differentiation, with integration, remember this deep dive.
Yeah, our source gave us this really tangible application. Figuring out how fast a plant drinks up nutrients,
Yeah.
and the total amount it gets.
It makes you think, doesn't it? What other rates of change? What other total amounts building up? What else out there in the world around you could we potentially understand better using these powerful tools from calculus?
Hmm. Once you start looking, you see them everywhere. Population growth, water flow, economic trends.
Endless possibilities. Something to ponder. Thanks for diving in with us today.